Okay, so fortunately this was really bad timing for PD right before the end of the semester, but that's just kind of how it worked out. So I set up this recording to go through some sample problems that are very, very similar to the ones that you're going to be seeing on your test. All right, so you'll notice that the stem of the question probably is identical to something you're going to run into your test. It's just going to have a different number. All right, so you can follow along with how I set it up and then plug in your numbers. All right. At the very, very end of this, I'm also going to give some help with the part 2 of the test, because I know that's normally what we'll do with our last class session before a test. And I have it built in so that you don't have to watch all of this. You can fast forward, and I'll even have it so that, you can, based on selecting an answer, you can go to the beginning of that question. Of course, if you get to the test and you're just like, oh my God, I don't know what I'm doing, put it off, wait till Monday, and then we can work on it together, okay? So first things first, you are going to see a question that sounds like this. Which compound does not form and precipitate when reacted with sodium hydroxide? You guys have different choices, but everybody has this correct answer, NaNO3. We didn't get a chance to talk about this, so here's a freebie for you. Okay, so here's one of the questions from the test that I chose to do an example of. So you're going to see the prompt: in a spacecraft, this reaction occurs. This is the same reaction that is in your question. How many liters of carbon dioxide will 10.7 moles of lithium hydroxide absorb? All right. So this number is different than what your test says. So do not look for my answer as your correct answer. You've got to do it based on the number on your test. So first things first, let's get ourselves organized based on what this question is asking us. All right, so we've got how many liters? So our question is how many liters of carbon dioxide? And then we know 10.7 moles of lithium hydroxide. So our known substance is the 10.7 mole LiOH. All right, which means we are starting here. It's already in moles for us. Our ending point is going to be liters of CO2, which means we are going to end here. So this one is a two-step problem. We need to go from moles of lithium hydroxide to moles of CO2 using our molar ratio. So to set that up, I'm going to set up so 1 molar ratio. Start with your parentheses. All right. On the outside, you put your known, the 10.7 mole LiOH. All right. On the bottom inside the parentheses, the moles you're going to put in are also going to be that known. And then the top is going to be the moles of your unknown, so that's going to be the carbon dioxide. And our numbers, where do those numbers come from? Your balanced equation. So if I look at CO2, there's nothing up front, which means there's 1. If I look at lithium hydroxide, there are 2. All right. So that means when I calculate this out, it's going to be, those cancel. So it's going to be 10.7 times 1 divided by 2, or 5.35 moles of CO2. All right. Am I done? We still need to get this into liters. So now I'm at this point. All right, so I'm going to take that 5.35 and I'm going to multiply by 22.4. And that gives me something I need a calculator for. 119.84 liters carbon dioxide. All right, So those are the steps you take to get through this. Now you need to do it with the value you were given in your problem. All right, next one is you will see this. Consider the reaction H2 plus Cl2 makes 2HCl. So hydrogen plus chlorine makes hydrochloric acid. How many liters of hydrochloric acid are produced when 68 liters of chlorine are reacted with excess oxygen? All right, so again, get yourself organized. What is our known substance? All right, so this question says how many liters of HCl? So we don't know that, that's what we have to ask, when there's 68 liters of chlorine. So our known substance is the 68 liters of chlorine. Our unknown substance is some liters of hydrochloric acid. All right. So that means since we're in liters, we're starting from volume and we're going to volume. All right. So step 1 is going to be volume to moles for Cl2. All right, so I'm going to take that 68 liters and I am going to divide by 22.4. And that gives me 3.04 moles of Cl2. All right, so this step done. Next step, molar ratio. I need to convert from moles of Cl2 to moles of HCl. So I'm going to start by setting up my parentheses, and then what goes on the outside? It's going to be your known moles. All right, so it's going to be that number we just calculated, the 3.04 moles of chlorine. All right, which means that's also going to be, at least the moles of Cl2 is going to go on the bottom. The number will come from somewhere else. And I need to turn that into moles of HCl. All right, where do those numbers come from again? Balanced chemical equation. All right, so if I look at HCl, that's a 2. If I look at Cl2, there's nothing there, so that's a 1. So this, my moles of Cl2 cancel, so I set this up right. Be 3.04 times 2 over 1, which is going to be 6.08 moles HCl. And now my last step, moles to volume. All right, so I'm going to take my 6.08 moles of hydrochloric acid. I am going to multiply by 22.4. And I get 136.19 liters of CO2. All right. So, again, just keep in mind your number here is different. Do this with your number, but the steps you're going to take are going to be the same. All right, we got another one. When aluminum oxidizes in air, it forms aluminum oxide. We've seen this one a few times. If an 85-gram sheet of aluminum oxide formed completely in excess oxygen, how many grams of aluminum were oxidized? All right, so let's start by breaking this down. All right, what do I know? We know that I have 85 grams aluminum oxide. All right, so that's my known substance. Question is, how many grams of aluminum were oxidized? So the unknown is how many grams of aluminum. All right, so call this a mass-to-mass problem because we have grams and we need to calculate grams. So that means you are going from here to here. So, step 1. Let's convert that mass to moles. All right. Now, that has a little bit of extra work to it because we need to calculate your molar mass. All right. So it's kind of like we have a 1A and a 1B. So 1A, molar mass, Al2O3. All right, I'm going to look up aluminum. That is 27 grams. And there's 2 of those, which makes 54. And then oxygen is 16, and there's 3 of those, which makes 32, 48. And if I total those up, I get 102. All right, and then 1B is going to be actually going from mass to moles. And that's where I'm going to divide by that molar mass I just calculated. So 85 grams divided by 102 is equal to 0.833 moles. Okay, step 1 done. Step 2. All right, that's here. This is our molar ratio. I'm going to set up my parentheses. What's going to go on the outside? That's going to be my known, and my known amount in moles. Oh, and I should have written down that this was Al2O3 here. So 0.833 mole Al2O3, which means that moles of Al2O3 goes in the bottom. That way they'll cancel. On top, we're going to put moles of aluminum because that's what my question needs me to solve for. All right. My numbers come from my balanced equation. All right, I see a 4 out in front of aluminum, and then there's nothing in front of Al2O3, so that's going to be a 1. So this is going to be equal to 0.833 times 4 divided by 1, which equals 3.33 moles of aluminum. Okay, we're getting there. I need some more space. Step 3. We are here now. All right, this is going to be moles to mass for aluminum. So 3A, your molar mass of aluminum. This one's nice and easy. All I gotta do is go look it up, and we actually technically already know that. Equals 27 grams per mole. So 3B, the actual mole to mass, I am going to take that 3.33, multiply it by 27, and that is going to give me 90 grams of aluminum. All right, so again, remember these numbers that I'm getting are not the number that you're looking for on your test, but this is the exact same set of steps that you'll go through. You just got to use your starting mass. Okay, so now we're talking about the part 2 of the test. This one, I'm not going to do every component of it for you because this matches the test exactly. So I'm just going to kind of walk you through what needs to be done. So you've got ibuprofen. It's the active ingredient in many non-prescription pain relievers. Each tablet contains 200 milligrams. This is an important number. Note the milligrams of ibuprofen. And a typical adult dose is 2 tablets. This is also important information. So first thing first is calculate your molar mass of ibuprofen. All right, so this is where you're going to go look up the mass of carbon, hydrogen, and oxygen off your periodic table. And then you're going to multiply them by how many exist. And then add it up. You should be able to handle that. All right. So then it says calculate the number of moles of ibuprofen in a single tablet. And this is where you got to do a little bit of work. All right. So 1 tablet equals 200 milligrams. All right. To be able to do your mole conversions, that needs to be in grams. So you got to divide this by 1,000 to convert it to grams. So you have 0.2 grams of ibuprofen. All right. And now you're doing a mass to moles conversion. Bring this guy in to help. All right, so you have mass. That's your 0.2 grams. And you need to convert it to moles. All right, so your molar mass is going to come from the question before that. And you're going to divide by that molar mass. All right, so you're going to divide this by the molar mass you got in the first part. It will be a tiny number. All right, very, very tiny number. Finally, the last part, calculate the number of moles of ibuprofen that an adult would take if she took 4 doses of ibuprofen in one day. All right. My hint here, it's 4 doses, not 4 pills. How many pills total are in 4 doses? Once you figure that out, all you gotta do is multiply that by the moles in 1 pill. All right, question 2 is sulfur dioxide gas reacts with excess oxygen gas and excess liquid water to form liquid sulfuric acid. In a laboratory, a chemist carries out this reaction with 73.8 liters of sulfur dioxide and gets 250 grams of sulfuric acid. So this one I did select a different number than you're going to see on your test. So I will do this one completely. You just got to do it. Show me your work for your problem when you do yours. So first things first, this one you got to balance. All right, so read through your information carefully, we've got sulfur dioxide reacts with excess oxygen and water. So we've got 3 reactants. SO2 plus O2 plus H2O to form liquid sulfuric acid. We have 1 product. All right, so first things first, what's not balanced? Let's see. This one's a little bit of a tricky one. You got oxygen in a lot of places. S, H, and O. S, H, O. So I've got 1 S, 2 hydrogens, 1, 2, 3, 4, 5 oxygens. And then on this side, I've got 1 S, 2 hydrogens, and 4 oxygens. So oxygen is not right. Okay. So, oh, and I just drew 1 too many. 4 oxygens. I have no easy way to turn 4 into 5. So I'm just going to double how many sulfuric acids we make. We're going to have to make more than 1 for this to work out. So that means I'm going to have 2 sulfurs, I'm going to have 4 hydrogens, and I'm going to have 8 oxygens. So now, let's see how I can fix these other things. I'm going to need to make 2 of these. That's going to make it so that I have 2 sulfurs, and then I'm going to have 4, 5, 6, 7 oxygens. And then I need to make it so that I have 4 hydrogens. So if I put a 2 there, that's going to give me 4 hydrogens. And then total I have 4, 6, 8 oxygens. Oops, I already drew too many. All right. So there's your balanced equation. So calculating theoretical yield, that's what we've been doing a bunch of different times. Let's see, I'm going to give myself some more space here. Oops, that's not what I want. Okay. So now that we have some space with which to do this, paste. Let's get ourselves organized. What do I know? I know that you start out with 73.8 liters of sulfur dioxide gas. All right, so I'm starting out in volume. And then it tells me that I get 250 grams of sulfuric acid. Whoa. Sorry. But that's my actual yield. That's going to come in handy when we have to do this percent yield. What I need to do is calculate my theoretical yield, so I need to put that into mass as well so that I can compare it to that 250. All right, so my question is grams of H2SO4. All right, so first step is volume to moles for the SO2. All right, so I'm going to divide by 22.4. So 73.8 divided by 22.4 is going to be equal to 3.29 moles of SO2. All right, so I have done that. Now I need to do my molar ratio. So I'm going to set up my parentheses. And on the outside, I'm going to put my known value, the 3.29 moles SO2. Moles of SO2 is going to go in the bottom. And I want to know sulfuric acid. All right, so moles H2SO4 is going to go on top. And then I go to my balanced equation to look for my coefficients. They both happen to be 2. All right, which kind of makes this easy. I'm going to do 3.29 times 2 divided by 2. So that's 3.29 moles. All right, almost there. So we got that step done, that step done. Now we need to get to our mass of sulfuric acid. So three moles to mass H2SO4. So 3A molar mass. So we know H is 1, there's 2 of those. S is 32 and there's only 1. And O is 16 and there are 4, which makes 64. So 64 and 32 is 96. So it's 98 grams per mole. All right, and 3B is the actual calculation. I'm going to multiply my 3.29 times 98 to get a calculator. $322.87 grams. All right, so I was thinking I could get 322.87 grams, but I only got 250. Which means now we can do our percent yield. All right, so we're going to take our actual value, the 250, divide it by what we thought we were going to get, multiply by 100, and you get 250 divided by 322.7 times 100, which is a 77% yield, which is not too bad. All right, I hope this helped. If you have further questions, see me on Monday. I'm happy to help.